This is the video on exploring polynomial functions in factored form. So this warm-up here, some of the slides are completed because I completed them in class. I'll just go over the answers again, and then the slides I didn't complete in class will be blank, and I'll give the answers to those slides. So the leading coefficient here is 1/2. The degree, if I multiply x times x times x, I get x cubed. The degree is 3. I could equate the function to 0 to find the 0. So equate each factor to 0. X plus 1 equals 0. Or x plus 5 equals 0. Or x minus 2 equals 0. You get x equal -1, x equal -5, and x equal 2. If you write it as an ordered pair, it would be -1, 0, -5, 0, and 2, 0. And the decreasing interval is from here to here. So from -3.361 to 0.694, you write the x values there. Here it is, the interval notation. -3.361 to 0.694. The end behavior as x approaches -infinity, f of x approaches -infinity, and then on the right, as x approaches infinity, f of x approaches infinity. The relative maximum occurs at 10.373, that's the y value. Or if you write it as an ordered pair, -3.361 and 10.373. The relative minimum, the y value is -6.299. Or if you write it as an ordered pair, 0.694 and -6.299. The increasing intervals, so from -infinity to this x value, -3.361, and then from this x value, 0.694, all the way to the right, which would be to infinity. So there's two increasing intervals. Here they are, -infinity to -3.361, and from 0.694 to infinity. Slide 2 is just the objective. Students will be able to sketch the graph of a polynomial function in factor form using zeros, multiplicity, end behavior, and the y-intercept. Slide 3 is just some terms. The maximum number of turning points of a polynomial function. The maximum number of turning points of a polynomial function is always one less than the degree of the function. The turning points look like this, from increasing to decreasing, or from decreasing to increasing, increasing to decreasing, decreasing to increasing. Those are turning points. You can also have a turning point if it's a point of inflection, concave up to concave down, or vice versa. The degree of the polynomial is most likely 4 because there are 3 turns in that function there. The fundamental theorem algebra says that an nth degree polynomial function with complex coefficients has exactly n zeros in the set of complex numbers, counting the repeated zeros. So in other words, the number of solution matches the degree, including complex zeros and repeated zeros. So multiplicity has to do with repeated zeros. The exponent of a factor of a polynomial function is called multiplicity of the corresponding zero. For example, if I have y equal x plus 1 cubed, then -1 is a zero of this function, and it has a multiplicity of 3. There would be a triple root, or the repeated zero would be -1. It occurs 3 times. And then a zero multiplicity 2 is called a double root. So -1 here is a triple root. -1 would have a multiplicity of 3. How does the multiplicity of a zero impact the graph? If the graph crosses the x-axis and appears almost linear at the x-intercept, it is a single zero. If the graph touches the x-axis and bounces off the axis, the zero has even multiplicity. And if the graph crosses the x-axis at a zero, zero with odd multiplicity. So it says here that the above graph has the degree of 6. So find the multiplicity. This is going to be even multiplicity. So if we call that 2 there, this is crosses like in a line here. So -1 has multiplicity 1, and then 4 has odd multiplicity. Since this is 2, if I call this 2 and I call this 1, then this would have a multiplicity of 3. And so -3 has a multiplicity of 2, -1 has a multiplicity of 1, and 4 has a multiplicity of 3. The number of zeros here would be 2 plus 1 plus 3, which is 6, and 6 matches the degree of the function. In the graph, there are 5 turning points, 1 less than the degree. So the turning points are 1 here, 2 here, 3 here, and this counts as 2 because this is going from concave down to a flat and then concave up. So this is 2 turning points here, 1, 2, 3, 4, 5. As degree 6 and 5 turning points. And this is an example of multiplicity here. So all these functions right here have a -1 as 0 or root. -1 has a multiplicity of 1 here. Here it has -1 has a multiplicity of 2. Here -1 has a multiplicity of 3. So each of the graphs have a 0 at -1. The multiplicity of -1 in the first graph is 1. The graph is linear at x equals -1. And the multiplicity of -1 in the second graph is 2. The graph bounces off the x-axis at -1. So here's the root, -1. Multiplicity of 2 makes this graph bounce off the x-axis. And then the multiplicity of -1 in the third graph is 3. The graph crosses the x-axis at -1 at a point of inflection. A point of inflection is a point where the graph goes from concave up to concave down or vice versa. In this case, the graph goes from concave down to concave up. So here's the root, -1, and then this part of the graph is concave down, and then it switches to concave up. And it has multiplicity of 3. Actually, 2 turning points, 1 here and 1 here. All right, now first practice problem. X times x is x squared. The coefficient would be 1, leading coefficient 1. The degree would be 2. The zeros are at -1. -1 plus 1 would be a 0, and then 2 minus 2 would be a 0. So -1 and 2, or if I equate each factor to 0 and solve, I have x equal -1 and x equal 2. This is a even degree with a positive leading coefficient, so both ends go up there. And then find the y-intercept. You plug a 0 in for x. You get -2, and then halfway between the first and second point, there would be halfway between 1 and, let me say that again, halfway between -1 and +2 is 1/2. So plug a 1/2 in for x, and the y value is -2.25. The maximum number of turns is the degree, which is 2 minus 1. Maximum amount of turns is 1. Plotting the critical points. The zeros are at 1 and -2. The y-intercept is at -2. And then I plotted this point 1/2, -2.25. And then from the from the zeros, both ends go up, and then connect the rest of the points together. And you get that parabola shape there. And practice problem 2 here. The leading coefficient would be 1 again. The degree is 3, and just to multiply everything together, I actually get x cubed plus x minus 2. So I can see the degree is 3 if I multiply it all out. You don't have to do that. If you just look at this exponent, x squared times x gives me an x cubed there, and the degree is 3. So leading coefficient positive, odd degree. This would be the end behavior. And then -1 has a multiplicity of 2, and 2 has a multiplicity of 1. On the x-intercept, plug a 0 in for y, get -2. Halfway between -1 and 2 is 1/2 again. Plug a 1/2 in, I get -3.375. The maximum number turns, the degree -1. And then plotting the critical points here, the zeros, -1 and +2. Y-intercept is at -2, and then 1/2 and 3.375 is right here. And if you happen to plug in a 1 for x here, you get 1 plus 1 is 2, 2 squared is 4, and then 1 minus 2 is -1. 4 times -1 is -4. So this point right here is 1, -4. You might not have known that, but I knew from graphing this that this was the relative min here, 1, -4. So you don't have to include that point, but if you do, it makes your graph more accurate there. Just want you to get the shape correct and the x and y intercepts correct, and maybe one other point on the graph. Practice problem 3. Leading coefficient 1 again, and then x cubed times x is x to the 4th, so the degree is 4. I have leading coefficient of 1, a positive, and then degree is even, so both ends go up there. -1 has a multiplicity of 3, and 2 has a multiplicity of 1. The y-intercept, plug in a 0, I get -2. And then halfway between -1 and 2 is still 1/2. Get -5.625, -5.0625. So I plot the intercepts, -1 and +2. The y-intercept is -2. And then 1/2 and -5.0625 is right in this area here. Just trying to get the shape. So this comes down like this, and then we're going to have a point of inflection here. So a turn and a turn, and then through 0, 2, through this point, and then both ends of the graph should go up. Even degree and positive leading coefficient. All right, problem 4. If I multiply all these together, x cubed times x is x to the 4th times x is x to the 5th. The leading coefficient is still 1 in this problem. Degree is 5. So x cubed times x is x to the 4th times x is x to the 5th. So leading coefficient is positive. Degree is 5. The end behavior looks like this here. The zeros, -1 has a multiplicity of 3. 2 has a multiplicity of 1. And 1 has a multiplicity of 1. y-intercept, plug in a 0 for x, 0 plus 1 cubed, and then times 0 minus 2 times 0 minus 1. And you get 2 for the y-intercept. So let's go ahead and plot the zeros first. Negative 1, 2, and positive 1. So halfway between negative 1 and positive 1 is 0. We already know what that is. It's 2. So we want to do 0 cubed, 0 minus 2, and 0 minus 1. So 0, 2. And then between these two zeros, between 1 and 2 is 1.5. So 1.5 plus 1 cubed. And then 1.5 minus 2 and 1.5 minus 1. And the maximum number of turns here would be 5 minus 1, which is 4. All right, so by the end behavior, I know this is going like this here. And this end is going down. And then a negative 1 has a multiplicity of 3. And 2 has a multiplicity of 1. Let's see here. So just to get a better idea, just do negative 0.5 here. So this goes up to here. So you go like this. The y-intercept is 2. I was wondering what was going on there. So let's get rid of this point. And plot this one. All right, so this, let me do this over again here. Yeah. All right, so this is going to come up like this here. Let me erase this a second. So you got this coming up like this, concave down, and then it's going to make a turn concave up. And if I make this positive 0.5, see what happens there. So 2.5. So we go up here, and down. And halfway between 1 and 2. I already had that value somewhere. Here it is, negative 3.9. So about here. So it comes down here, and then turn. So it's not the best sketch, but it gives you an idea of the shape there. Let's come up here, point of an inflection, then up to some relative max, down here until a relative min, and then the left side goes down and the right side goes up. All right, here, the coefficient of 1 degree would be x cubed times x squared, so 5. And the end behavior, same as the last graph. This is negative 1 as a multiplicity of 3 right here, and then 2 as a multiplicity of 2. Y-intercept is 0 plus 1 cubed and times 0 minus 2 squared. And I get a 4 there. Y-intercept 4. X-intercepts of negative 1 and 2. And a point between negative 1 and 2 is 1/2. For the x value, 1/2 plus 1 cubed. And then times 1/2 minus 2. Negative 5.0625 down here somewhere. And negative 1 has a multiplicity of 3. So we start down this way. The left side's going down. So like this. And then a point of inflection here. Whoops. Let's undo that. So let's go like this. and then a point of inflection here, 0, 5, then a turn on this way, the maximum number of turns is 4. And let's see what happens if I put in like, say a 5 here. Let's not put it in that. Let's put in a 3. So 3. Should be a square there. I think I got the wrong value for 1/2 here. This is annoying here. So 3, I get a 64. So way up that way somewhere. And then 1/2. Yeah, I had the wrong value for 1/2. So let's erase this point. So 1/2 and about 7.5 here. 1/2, 7.5. There we go. So let's try this again. So this goes up. The right side is going up. The left side goes down. And this has a point of inflection because it has a odd multiplicity. So something like this here. Let me try this again. So like this, and then a point of inflection, and then keep going up. Whoop. If I could use the mouse here a little bit better, it's a little more steady of hand here. So point of inflection. This continues up here. Continues up, and then multiplicity at 2 will bounce off the x-axis. So so that looks like that somehow. So the shape is correct. And if you wanted to help yourself a little bit and check against graphing calculator here. Let me go to Desmos here. So x plus 1 cubed and x minus 2 squared. All right, so it goes up much higher than what I have, but notice that this has a point of inflection at -1, and then 0, 4, and 2, 0. I just don't have this point as high, but I have the right shape. So that's what I'm looking for on your sketch, is the right shape there. It's hard to draw the point of inflection, but there should be one right here. So there's what the Desmos calculator says. There's our graph. I wanted to be a little bit more accurate, then I would do this here. Erase this here. And have this increasing more rapidly. So it goes like this. Yeah. It's hard to have a steady hand there to try to push the mouse there, but and problem 10, leading coefficient 1, degree is 5. The zeros, -1 has a multiplicity of 3. And so positively in coefficient, odd degree is this one. And to find the other zeros here, I would plug into the quadratic formula. So in other words, you have x squared plus x plus 1 equals 0. So a equal 1, b equal 1, and c equal 1. So plug into the quadratic. So -1 plus or minus square root. 1 squared is 1. 1 is 4 times 1 times 1 divided by 2. And x equal -1 plus or minus square root of -3 would be I square root of 3. Divided by 2. The y-intercept, plugging in a 0 for x. And 0 squared plus 0 plus 1. And you get 1 for the y-intercept. The maximum number of turns is 4. So the only 0 I have is -1, and as a multiplicity of 3, the y-intercept is 1. All right, so this right side goes up. And at -1, you have a multiplicity of 3, so it's going to be a point of inflection there. So go like this, and then something like that. So that problem has complex roots there. Here, the leading coefficient is 1/4. The degree is 3. The zeros are at 0, 2, and -3. And all of them have a multiplicity of 1. The y-intercept, 1/4 times 0. 0 minus 2. 0 plus 3. And you're going to get 0 because these two multiply together is 0. 0 times anything is 0. So 0, and 2, and 3. -3, sorry. So you have leading coefficient 1/4, positive. Degree is odd. And then find a point halfway between -3 and 0. Would be -1.5 for x. Like a -1.5 in for x. So 1/4 times 1.5 times -1.5 minus 2 times -1.5 plus 3. So at -1.5, you get about 2 somewhere in here. And then halfway between 0 and 2 would be 1. So 1/4 times 1 times 1 minus 2 times 1 plus 3. is -1. All right, each of the zeros has a multiplicity of 1. So, and this side goes up. This side goes down. And then connect these together. Oh, and the maximum number of turns would be 4. Because the degree, well, degree is 3, so sorry about that. That's 2. And there are 2 turns here. 1, 2. Next to practice problem 2. Getting coefficient -2/5. Degree is 1, 3, and 2. So 4, 5 again. One has a multiplicity of 2. And -3. And 0. And so negative leading coefficient and odd is that one. A y-intercept is 0. You plug a 0 in here and multiply it out, you get a 0. And so 1, -3, and 0. So halfway between -3 and 0 is -1.5. And then 1.5 minus 1. Squared. And 1.5 plus 3. Squared. And then halfway between 0 and 1 would be a half. So this should be negative. Here. What's going on here? Negative. Make this negative. Make this negative. So 8.4. So 1.5, negative 1.5, and 5, 6, 7, 8 up there somewhere. And at 1/2, I got right in here. So negative 3 has a multiplicity of 2, and this end goes up. Bounces off the x-axis here, and then up to here, and then back down. And 0 has a multiplicity of 1, and 1 has a multiplicity of 2. So let's plug in another point in here. Say 4. Let's do 2. So this goes down. Like this. And then this one has a leading coefficient of 1, degree of 4. So leading coefficient positive and degree even. Both ends go up. Zeros. Negative 2 has a multiplicity of 2. And then if you equate the second factor to 0, I'm going to get imaginary solutions here. So this x squared plus x plus 2 equals 0. A is 1, B equal 1, and C equal 2. We have negative 1 plus or minus square root. 1 squared would be 1 minus 4 times 1 times 2. And divide that by 2. One 41 square root. Well, it's going to be a square root of negative 7. So I square root 7 divided by 2. So you get complex solutions there. The y-intercept. Zero plus 2 squared. 0 squared plus 0 plus 2 is 8. So the y-intercept is 8. The x-intercept is negative 2 as a multiplicity of 2. Both ends are going to go up. So this flattens out here. We do this again. Maximum number of turns is 3. And the last slide is the exit ticket.